If you clicked on this video, then you want the answer to one question: what is an observer in quantum mechanics? This is a question that has baffled physicists for over a century, and has led to even more confusing questions like, is Schrodinger's cat both alive and dead? How is that possible? What is the role of consciousness and subjectivity in the measurement collapse problem? Do we live in a multiverse or many worlds? I'm theoretical physicist Dr. Shannon Ray, and for the last 7 years I worked as a quantum information theorist, where every day it was my job to ask the question, what is quantum mechanics? And in this video, I'm going to give you the answer to all of these questions using the simple concept that there's no objective up in the universe. So if you want to find out how that truth answers all of these questions, stay tuned until the end of the video. Welcome to the Bottom Turtle channel. Hello everybody, welcome back to the channel. I'm theoretical physicist Dr. Shannon Ray, and in this video, I'm going to continue on my goal to reconceptualize all of reality using nothing but the concept of information. So if you've been watching the channel so far, you know that I associate entropy with symmetry, and I associate information with broken symmetry. So when I say that I'm going to reconceptualize all of reality using nothing but the concept of information, I'm saying that the relationships I create between entropy and symmetry and information and broken symmetry allow me to extend the concept of information to the concept of symmetry. And so to explain reality using symmetry is to explain reality using information. And this is an algebraic transformation. And so I'm not substantiating that claim right now, but as you watch this channel, you will notice how I'm merely saying the exact same thing in a different way. That is, I'm never saying anything new, but I'm saying it in a new way. And this is associated with a change in perception, which is associated with algebra. And this is going to be a deep theme in today's episode, where I explain the idea of the observer in quantum mechanics. That is, I think that I have actually figured out what constitutes an observer in quantum mechanics, what the role of the observer is when creating reality, and how all of this is associated with subjectivity. But ultimately, that subjectivity is associated with perception, and that perception is physical. So in today's episode, I'm going to explain all of this using the experimental measurement of a qubit. So just using the concept of measuring a qubit, I think that I can explain in very simple terms what constitutes an observer, what the observer's role is in creating reality, how reality is fundamentally determined by subjective perception, which actually has a physical content to it. Before we jump into the video, don't forget to like this video, subscribe to the channel, and share it with a friend. Remember, my goal is to become an independent researcher so that I can continue my research and share these ideas with you. So if you like this content, remember, every like, share, comment, and subscribe is like donating to my research fund, and every donation counts, and I really appreciate it. So with that, let's jump into it. To understand the role and the nature of the observer in quantum mechanics and how it's associated with the physical nature of perception, I first want to look at the example of measuring a qubit, since it's the simplest example that shows how the observer is involved in creating reality. So the first thing we need to do is understand how information is stored and extracted from a state of a qubit. This is because, as I stated in my previous video on information and broken symmetry, to have information is to be able to predict the future. This means that the information in the qubit tells us which reality is most likely to come into existence. As many of you may know, quantum states differ from classical states because they can be found in something called a superposition, where it's in two states at once. In this case, I've written psi as a superposition between the states 0 and 1. But in the language of linear algebra, this is just a vector. And the coefficient alpha represents the length of the vector in the 0 direction, and the coefficient beta represents the length of the vector in the 1 direction. But these coefficients don't only represent length, they also represent probability, where alpha represents the probability of measuring 0 given the state psi, and beta represents the probability of measuring 1 given the state psi. This is the information that's contained in the quantum state, and these probabilities are computed using the Born rule, which is one of the fundamental postulates of quantum mechanics. So the information is stored in the state using a vector, and the information is extracted from the state using the Born rule. So far, everything I've said is basic quantum theory and isn't very interesting. But what is interesting is that this quantum state doesn't have any information in it at all. And that's something you probably won't hear most physicists saying. But I'm saying this because the state has to be defined with respect to some basis. And as I'll argue, this basis doesn't have any physical meaning without the existence of an external observer. Recall from my last video that the state of a qubit can be described by a point on the surface of the Bloch sphere. From here, we see that different choices of theta and phi, which chooses a different point, results in different probabilities of measuring 0 or 1. But the problem with this is what determines the orientation of the axes, which in turn determines the angles, thus determining the statistics and information of the state. The answer to this question is the orientation of the detector, which is external to the system. If we had two observers and each of them had different orientations of the detector, then they would observe different statistics when measuring the state, despite the fact that the state is the same. This freedom in orienting their measurement device is a freedom in how they represent their quantum system. But this freedom can actually change what physical realities are created. Imagine we had a Schrödinger cat-like example, where a cat lives if we measure up along the detector, and a cat dies if we measure down along the detector. And then imagine that we have two realities, one where the observer aligns their detector with the orientation of the qubit, and one where the observer aligns their detector in the opposite orientation of the qubit. In the first reality, the cat is guaranteed to live with 100% certainty, and in the second reality, the cat is guaranteed to die with 100% certainty. This tells us that what really matters is the relative orientation between the system and the detector, and that different choices of representation actually affect which realities come into existence. This means that if we change the orientation of the state by changing the procedure for which it's prepared, thus choosing a different point on the Bloch sphere, but keep the orientation of our detector fixed, then the statistics of what we observe changes, which means that the information in the state changes. But also, if we leave the procedure that produces the state the same, which is to say we choose a specific point on the Bloch sphere, but we change the orientation of the detector, then the observed statistics also change, which means that changing the orientation of the detector actually changes the information that's contained in the quantum state. This is why I said before that the quantum state itself doesn't have information without an external observer, because what is observed actually depends on the relative relationship between detector and the system. The reason why we have all this freedom is because all of these orientations are related by a symmetry transformation, and the symmetry group associated with the Hilbert space of a qubit is SU2. And so, because they're all related by a symmetry transformation, then that means they must be treated symmetrically, which means that they're all equally valid. This is why we have this freedom. But what this also means is that a change in orientation is merely a change in perspective. But as we just saw, this change in perspective changes what physical realities are created. The observer actually imbues information on the quantum state by being external to the system. This is the observer's role in quantum mechanics. It has an effect on what realities are created. In the previous section I showed that the state of the quantum system has no meaning or no information without its relationship to the detector. And this is because without an external detector, all of the points on the Bloch sphere must be treated as symmetric, which is to say they must all represent the same reality. But this should be confusing and paradoxical because we know that if we keep the orientation of the detector fixed, but we change the state of the system by selecting different values of theta and phi, we can go from realities where the cat is guaranteed to live to realities where the cat is guaranteed to die. So how can these realities be considered the same? The answer to this question is precisely the answer to what constitutes an observer in quantum mechanics. And the answer is this. An observer is that which breaks symmetry, thus allowing the different points on the Bloch sphere to be distinguishable as different physical realities. And as I'm about to argue, this implies that the observer must be external to the system. If we observe the Bloch sphere in isolation such that it's been removed from any external reference, then that means that all orientations of the Bloch sphere, that is, all points on the Bloch sphere, must be treated as symmetric and identical. Because remember, the idea of a symmetry transformation is when you do a transformation, you can't tell that anything has happened. But you might think to yourself, let's consider something like a small protrusion coming out of one point on the Bloch sphere to represent its state. And if I were to rotate the Bloch sphere, then I could see that protrusion rotating. But the problem with this is that you are functioning as an external observer during this transformation. To understand why these all must be treated the same, imagine that there is a continuum of invisible observers that are all equal distance away from the block sphere, such that when the orientation of the sphere rotates, from one observer's perspective, the orientation is rotating, but from another observer's perspective, the new orientation is identical to a previous observer's perspective. What this means is that the illusion and broken symmetry, based on the observation in a change in orientation, can only be a matter of perspective. But it's these differences in perspective that are precisely related to the difference in orientation between the detector and the state, which we know for a fact result in different observed realities. This should be mind-blowing, because we know that the different orientations of the protrusion must be treated equivalently. Otherwise, you're saying something like one of these observers' perspective is more real than the other. But in actuality, we know that rotating the state is a symmetry transformation, which means that when you do the transformation, nothing is happening at all. So to understand why all of this implies that the observer must be external, I want to go back to the examples that I used in my video on information and broken symmetry. Remember that I had a two-dimensional surface where all the points were perfectly identical, meaning if I were to do some sort of transformation of this surface by moving it from left to right or rotating it, you can't tell that anything has happened. So what I did is I created a circle of points on the surface so that now if I move the surface, I can tell that something is happening. But the only reason why this is possible is because, again, you are functioning as an external observer. If what only existed was a two-dimensional surface, meaning that all observers must exist on the surface, then when the surface is transformed, then you would be transformed with the surface, and thus you couldn't tell anything was happening, whether there was a circle there or not. But what's implicitly happening is there is some external space, something external to the two-dimensional surface that allows you to look down on the surface. So it's almost like the two-dimensional surface has an x-axis and a y-axis, but you exist in some vertical z direction that allows you to look down on the surface so that when it moves, you are allowed to remain fixed. And this is the essence of an observer. The observer allows for the existence of a fixed point so that when a transformation occurs, you can see the relative relationship between your fixed point and the point that's moving. And this is what I demonstrated in the case of the circle. In the case of the circle, if all the points are identical, then when I rotate the circle about its axis, you can't tell anything is happening. But if I were to make one of the points blue, then when I rotate the circle, you can see the blue point moving, so you think symmetry is broken. But this is identical to the situation of the protrusion in the continuum of observers looking at the protrusion. If I rotate the circle in one direction, then from the perspective of some other observer, the new orientation looks identical to the previous orientation for some other observer. And so the only way for symmetry to be truly broken is if we have a fixed red point such that information emerges from the angle between the blue point and the red point. So this is one of the hallmarks of being an observer. It allows symmetry to be broken such that the different orientations now represent different realities, thus allowing the creation of information. So by being external, the observer also functions as an information creator. So by removing the sphere from any context, we create symmetry, and as such, the realities that emerge must be equivalent. Otherwise, you're saying that there's some information that can distinguish them from each other, which is simply not the case without some external reference. Now you might think to yourself, this scenario in which the sphere is totally isolated is just some thought experiment that you've made up and doesn't actually represent reality. But that's not the case. In quantum mechanics, a necessary condition for a state to be pure is that it's separable. This means that it has no correlations or is not entangled to the external environment. From the perspective of the quantum state, it is rotating in isolation. This is what the dynamics of the Schrödinger equation does. It does unitary transformations, which by definition are algebraic information-preserving symmetry transformations. And in fact, if a state does not remain isolated while it's evolving, then we have wave function collapse events. And as we've just discussed, the outcome of those events depends on the relative orientation between the system and the environment. Before I conclude this video, I want to talk about the relationship between symmetry and subjectivity. In the scenario where the Bloch sphere was isolated, there was no objective orientation of the z direction. All orientations of the z direction are equally equivalent. You can't distinguish one from the other. Saying that there is an objective orientation of the z direction is like saying there is an objective up direction in a completely empty space. And so if we think of the thought experiment of Alice and Bob floating in completely empty space, and imagine that for both of them, they view up as being the direction from their feet to their head, then if they're oriented differently with respect to each other, then they have two completely different notions of up, and there's nothing to say who's right and who's wrong. So in their scenario, they are stuck in a situation where up is entirely subjective. And this is due to the lack of anything breaking the symmetry that they can see beyond themselves. There's no stars, there's no planets, there's nothing outside of themselves that can give them any sense of orientation. So subjectivity gives rise to something like pure subjectivity. But if instead, imagine there was some sort of a large structure that suddenly emerged to one side of them, like an infinitely long plane that seemed to go on forever, then suddenly they would have some objective direction that is independent of their mere subjective opinion, which is to say, in this direction there's a giant mass, and in this direction there's nothing. But then imagine that suddenly that giant mass generated a gravitational field and pulled them toward it. So now they can stand on this structure. Now suddenly they both gain some sort of objective notion of up because both of their feet are on the surface. And this is essentially the scenario that we're in reality. The only reason why we have some sense of an objective up is because we are all entangled to an environment that seems to have a consistent structure and is predictable. And so because of that, the classical reality that we all live in gives us a notion of up. But even this notion of up isn't absolutely objective because our notion of up comes from the gravitational field of the Earth. We know that if we want to go up, then we have to do work against the gravitational field. And so what we have is a radial vector from the center of the Earth going outward, and anyone standing on the surface, their up is the outward radial direction. But for one person on one side of the planet and another person on the other side of the planet, what is up to one person is down to another. And even so, as we pan out from just our Earth, we see that our Earth is floating around in space. And so this scenario of a lack of objective up is actually the reality that we experience every day. And you can imagine, like, if we got rid of all of the stars, like if there was some pocket of space in which all directions looked the same, then we would be exactly in the scenario where there's no objective up. As I said in my previous videos, there isn't infinite energy and matter to create infinite symmetry breaking. This means that there's always symmetries that give rise to simultaneous realities. And these realities are the same and not the same. They're the same in that they're all related by symmetry transformation, but they're not the same in that the realities they create depend on the relative relationship between the system and some external observer that breaks symmetry. This means that looking at the symmetry from different perspectives actually gives rise to different realities. This is the physical nature of perspective or subjectivity. So that's my argument, everyone. An observer is simply that which is external to the system, which can then break symmetry, thus creating information and creating reality. And I use the example of a qubit to show that prior to measuring the qubit, it doesn't have any information because the outcome of the measurement entirely depends on the orientation of the measurement device or the observer. And so all of this is consistent with my larger view of quantum mechanics, which is that quantum mechanics is a consequence of a lack of information. And from that lack of information arises symmetries. And this is precisely what quantum states are. They are symmetries. When you're talking about what a qubit is SU2, because any concept of a state of the qubit is merely an idea of the orientation. But as we showed in the video, any transformation of the orientation in isolation without reference to anything else is merely a symmetry transformation which results in nothing happening. And so all orientations of the qubit, of a quantum state, that are a result of a unitary transformation by Schrödinger equation or whatever, is the same reality. So the lack of information results in a symmetry which results in simultaneous realities. And the difference from all of these simultaneous realities actually comes from the perspective of an observer. And this perspective is merely a subjective difference because we know that all of the orientations must be identical. And so what I'm saying is that it appears to me that quantum mechanics, or the observation of quantum mechanics, is the foundation of subjectivity and subjective freedom. How you perceive things affects how you create. And in the video, I didn't make a comment about whether or not the observer has to be conscious or not. At the moment, I don't think that it does. I think that it merely requires a difference in orientation, or a relative orientation, to allow for the creation of a state of reality. But what I will say is that all things that are conscious are observers. And so in my working model of reality, this ability for there to be freedom, subjective freedom, is actually the basis on how we're capable of creating reality and how we're involved in creating reality. Um, and so at the foundation of all of this is something like a paradox. Symmetry transformations are strange paradoxical objects, or strange paradoxical things, because they are defined by the fact that when you do the transformation, nothing's happening, which means that all elements of the symmetry must be identical. But at the same time, there's some sense in which they are not identical. And this can only occur when you have differences in perspective. And so this is why I think that at the foundation of subjectivity is actually physical reality. And this paradoxical nature, I would argue, is also the foundation of the essence of algebra, where the idea of algebra is to change something without changing it. You're merely multiplying by identity, or one. And one of the examples I like to use is the idea of the square root of 2 divided by the square root of 2. Now, if you take the square root of 2 divided by the square root of 2, and you multiply the numerator and the denominator by the square root of 2, what you get is 2 divided by 2 times the square root of 2. The 2's cancel, only leaving 1 over the square root of 2. If you put the square root of 2 over 2 next to 1 over the square root of 2, then you'll find that they're actually the same thing. They only look different. And so this nature of subjectivity, I think, is the nature of, in essence, of algebra. And as Anton Zeilinger and Nicholas Giffen point out, is that information is actually created at the moment of measurement. And so what we have is a situation where, in my interpretation of quantum mechanics, quantum states arise due to a lack of information. And when you make a measurement, you are actually creating information, which is to say you're actually creating reality. And this is what an observer is in quantum mechanics. It is actually the active participant that is involved in the process of creation. So I hope you guys liked the video. I hope that it was convincing. If you did like the video, don't forget to like the video and subscribe to the channel. Also, don't forget to make a comment in the comment section. If you think I'm full of crap, let me know. If you think that I have a good idea, also let me know. That could give myself a pat on the back. And if you know a physicist or a scientist or a philosopher friend, and you think that they would be interested in this, please share it with them and ask them if they think I'm full of crap or not. So with that, I appreciate you guys, and I'll see you in the next video. Stay turtling, my friends. Peace.